Over the past 100 years, our view of the universe has radically evolved. It was only in 1923 that Edwin Hubble realised there was more than just one galaxy. 100 years later, we now think there are hundreds of billions of galaxies within the observable universe. In 1929, it was also Edwin Hubble who realised that nearly all of these galaxies are moving away from us, discovering the universe's expansion. Until the late 1990s, it was thought that the expansion should be slowing down. Galaxies gravitate towards each other, and this attraction should work in an opposite direction to the universe's expansion. Observations now suggest that this is not the case. The expansion of the universe is getting faster. But what's causing this? Is there a simple explanation? To answer this, we first look to Einstein's equations. Einstein's field equations describe gravity. The left-hand side describes the curvature of the space-time manifold at a given point. The right-hand side is known as the stress-energy-momentum tensor and describes all the energy contents at that same place. Simply put, the more stuff we place somewhere, the more space-time will curve. These equations have a special feature. We're allowed to just add a constant term coupled to the metric, and these equations will still hold. This term will have a value the same everywhere in both space and time. In physics, if something can be added, it should be added, as it can always be removed later by setting it to 0. We will call this term the bare cosmological constant. To give an interpretation to this term, we must first consider the vacuum energy. In quantum field theory, the ground state or vacuum energy of a quantum field is non-zero. This can be thought of as the field's inability to sit exactly at the bottom of the potential well due to the uncertainty principle. The vacuum energy should, according to general relativity, curve spacetime. But how? What is the stress-energy-momentum tensor for the vacuum? In special relativity, it's said that the laws of physics are the same in all inertial frames of reference. Another way of thinking of this is to say that the vacuum is Lorentz invariant. In other words, the vacuum does not depend on how fast you're going relative to somebody else. All unaccelerated observers will agree on the vacuum energy. It turns out that the stress-energy-momentum tensor for a Lorentz invariant quantity must take this form, where ρ is the energy density of the vacuum. This looks just like the bare cosmological constant we introduced. When we combine the two, it's clear that these will oppose each other, and hence the bare cosmological constant can be interpreted as a correction or counter-term to the vacuum energy. The combination of these two terms is known as the effective cosmological constant, or simply just the cosmological constant, and it's this that gravitates. The cosmological constant's impact on the evolution of the universe is given by two equations. Firstly, this governs the speed of cosmological expansion in a flat universe, which we live in. It's clear to see that increasing the cosmological constant will increase the speed of expansion for a constant energy density. Secondly, we have the acceleration equation, which governs how this expansion will accelerate. Once again, we see that increasing the cosmological constant causes the universe's expansion to accelerate faster. If its magnitude is similar to the energy density of matter and radiation in the universe, then it will clearly have a large impact on the universe's evolution. Okay, so we know what the cosmological constant is. Can we now simply calculate the vacuum energy and fix the bare cosmological constant so that their sum matches observation? No, absolutely not. This is the cosmological constant problem. The reason why we can't do this is subtle. We can absolutely calculate the vacuum energy, and for a simple scalar field, it's given by this. The vacuum energy depends on the mass of the heaviest particle in nature to the power of 4. But what is this particle? Unfortunately, we have to guess. The lowest mass it could be is the energy scales probed at the LHC, and the highest is thought to be the Planck mass. Normally, this kind of guess is totally acceptable in physics and is common practice. For example, the quantum mechanical corrections to the mass of the electron due to its self-energy is given by this equation. See how it depends on the highest particle mass, m. The issue that arises with the cosmological constant that doesn't arise with the electron's mass is its sensitivity to m. Remember, to find what the cosmological constant is, we must first calculate the vacuum energy and then fix the bare cosmological constant to match this with observation. Say that we choose m to be the LHC scale, calculate the vacuum energy, and fix lambda bare. Imagine in the future, we then discover a new particle with a mass 10 times greater than our original m. This will require changing the vacuum energy accordingly. This is known as a change in the effective description. After this, the vacuum energy will massively change as it depends on the 4th power of this new mass. We cannot, however, change lambda bare to match this value, as once it's been set, it must stay at this value in accordance with renormalization. Therefore, after this, the predicted value for the cosmological constant will be massively off from observation. The discovery of the new particle will have a negligible change in the correction to the electron mass due to the logarithmic dependence on m, and therefore this will still agree with observation after a change in the effective description. The cosmological constant cannot do this. As well as being one of the deepest problems in physics, it's also one of the most misunderstood. The problem is usually framed as one of fine-tuning. The bare cosmological constant must match the vacuum energy for about 60 to 120 decimal places. After this long string of matching, it must then deviate to reproduce observations. Why does it not match it exactly? Surely we're not allowed to do this. As explained earlier, we are allowed to do this. Renormalization is at the heart of quantum field theory, where often infinities are subtracted. We're allowed to set the counter term to whatever we like, but it's only allowed to be set once and must hold for any change in the effective description. For the cosmological constant, this cannot be achieved whilst agreeing with observation. This is the cosmological constant problem.